In this video, I'll talk about valence bond theory, hybridization, sigma and pi bonds, and how you really make the sigma and pi bonds. Now, if you're learning valence bond theory and the hybridization concept, you should already know the Lewis-Strauss structures. Now, let me talk about the difference between the Lewis-Strauss structures and the valence bond theory. The Lewis-Strauss structures simply talks about how the bond is formed in terms of sharing the electrons. It does not actually talk about how in real life at the molecular level the bond is actually formed, but it's simply in a 2D representation of, hey, I got two atoms, they're going to be sharing the electrons, and those shared electrons are going to be making the bonds. But now, how exactly the bond was made, it does not have any clue. It does not explain that. And who explains that? Valence bond theory does a really good job in terms of explaining how the bond is actually formed. So I'm going to take few examples here, such as like H2, and I'll take an example of HCl, and I'll take an example of Cl2 as well, to explain the valence bond theory. Now remember, I'm not going to be going into too much of a details on the valence bond theory, just enough to just kind of an introductory chemistry topic. And I will be eventually talking about the hybridization and how hybridization actually helps the explanation in terms of making multiple bonds and all that, because the valence bond theory also has a little bit of limitations, but with the help of hybridizations, you can get a lot out of the valence bond theory. Now, suppose I have a hydrogen. Now, remember, hydrogen, I have one electron, so the electronic configuration is going to be 1s1. And for the chlorine, which has 17 electrons, so this is going to be the valence shell electronic configurations. I do not have 1s2, 2s2, 2p6 in there. I'm just worrying about what are the electrons going to be in the valence shell. So I have 7 electrons in the valence shell, and they're going to be filling in 3s2 and 3p5. So what that does, that leaves one orbital in the 3p half-filled, and I can say there is a half-filled orbital in the hydrogen as well. So a hydrogen, since it's filling 1s, it's going to be a sphere, because s orbitals are a sphere, and then the chlorine, the last electron I got in there, which is the half-filled orbital, is filling the p orbital, and the p orbitals are actually dumbbell in shape. So I'm kind of showing up here that I got one electron on the hydrogen atom, and I got one electron that's going to be half-filled or unpaired in one of those p orbitals at the end in the chlorine atom. Now we'll come back to that in a minute, but remember these are just the regular shapes of the s orbitals and the p orbitals. Now, when I'm making the hydrogen bond, the valence bond theory talks about the overlapping of orbitals that are actually half-filled, not fully filled, but rather the half-filled atomic orbitals. So when I'm making the hydrogen, and if you go back and look at, let's say, um, focus on just the electron dot structure or the loose dot structure for a hydrogen atom or hydrogen molecule rather, we know there is one valence electrons and we typically say, all right, I got one electron coming from one atom, another electron coming from another atom, then these electrons are being shared, and that's how we really make the bond. That is in a simple representation coming from the loose dot structures. It does not actually explains how the bond is actually made. So how do we get that explanation? Valence bond theory does a really good job in terms of explaining how the bond is really going to be made. So we have one orbital from the 1s orbital from the one of the electrons from one of the hydrogen atoms, so that has one electron, and I'm going to have another s orbital, and we're going to have an opposite spin. That's another postulates of the valence bond theory, that whenever you put together two atoms or to make a bond, their electrons will have an opposite spin. So I got one s orbital from one hydrogen atom, one s orbital from another hydrogen atom. Now they're actually going to be overlapping, and that's how you're going to be making the bond. So when they're overlapping, I'm going to have this guy, and I'm going to have another 1s orbital from the second hydrogen atom, and they're going to be overlapping. And while they are overlapping, you will see in an area where the electron could possibly be. So this area right there, I could have made this a little bit bigger, but I'm just going to make it a little bit bigger here. So this overlapping region is the one that describes the formation of the bond. And in this overlapping region, this is where your electron's going to be. So I'm going to have one electron pointed up and the other electron pointed down. And that's how you actually make the bond. Now, none of those things were actually talked about in the Lewis-Strauss structures. So valence bond theory does a really good job in terms of explaining how the bond is actually made. So you make this bond and eventually you will lower down the potential energy, and that is one of the other postulates of the valence bond theory. I'll talk about that in a minute, but let me go ahead and give you another example for the HCl. So for the HCl, we're going to have one s orbital from the hydrogen atom, and we're going to have one of the p orbitals from the chlorine's atom that is actually half-filled. Now remember, the valence bond theory talks about that you're only going to be overlapping the half-filled orbitals. So I got one half-filled orbital here in the 1s of the hydrogen, and I got one of the 3p orbitals that is half-filled in the chlorine. So those two guys are going to be overlapping here. So when they overlap, you make the bond here, and that's how you get the HCl. Now, if you go back and look at the Lewis-Strauss structure of HCl, we typically go like, all right, I got, in case of an HCl, how many valence electrons I have? I have 8 valence electrons, and we say, okay, we're going to make one bond between the two atoms, and then I want to make sure the octets is completed. That was another thing about the electron dot structures, so that it kind of explains the octets, the resonances, the formal charge, and whatnot, and everything. So those remaining 6 electrons out of those total eight valence electrons will go on to the chlorines as a lone pair. But then how this bond was actually made, it didn't really explain that. And that's how the explanation comes in, that there is going to be an overlapping of one s orbital from the hydrogen atom and one of the 3p orbitals from the chlorine. So remember, your hydrogen atom is a sphere, your p orbital or your s orbital is in a sphere, and your p orbital from the chlorine is actually in a dumbbell. So you get this end-to-end overlapping, and this is how you actually make a sigma bond as well. So whatever you're making right here is going to be the sigma bond, and this right here that you made is also going to be in a sigma bond, which is actually in a single bond. I will talk about the sigma bond again in a little bit, but that's how you really make the sigma bonds. And you will learn a little bit later on that you don't necessarily have to have these orbitals kind of staying in their original shape using the hybridization concept. But for right now, remember that whenever you have the end-to-end overlapping, you eventually ended up making a sigma bond. But we will talk a little bit more in details about how the sigma bond is actually made from the hybrid orbitals. If I take another example of, let's say, chlorine. So in case of chlorine, when we draw the Lewis-Strauss structures, we are more concerned about making sure all of your octets are completed, everyone is happy in terms of formal charges and whatnot, and it just shows the bond between the two atoms. So chlorine, each chlorine has 7 valence electrons, so the total valence electrons would be 14 here. So I'll go ahead and put one bond between the two chlorine atoms, and that uses up 2 electrons. So I still have 12 more to go, and then we go like, all right, we want to go ahead and complete the octets for all the chlorines there, and that uses up the remaining 12 electrons. And this explains the octet. Both of the chlorines are happy. This explains that there is a bond made between the chlorines, but it doesn't really explain how the bond is actually made. So this is where the valence bond theory comes in. We're like, all right, I got this one of the p orbitals that has one electron in the chlorine, another p orbitals from the second chlorine that has one electron. Those are the one that's going to be overlapping, and these overlapping these overlapping atomic orbitals eventually going to make the bond between the chlorine atoms. That is the whole point in the valence bond theory. So some of the postulates that you have in the valence bond theory, that the, the bond is going to be formed when you have half-filled atomic orbitals between the two atoms that are going to be overlapping with one another. So we talked about that. We also talked about that the electrons that are going to be shared, they must have opposite spin at the end of the day. And the strength of the bond formed typically or can be estimated, whether it's like quantized, you could eventually quantize the strength of the bond, but we're not going to be talking about anything close to that. But you can say that how strong the bond is going to be is determined by the strength of overlapping regions, basically, or how much overlapping region there really is. And then typically the energy is released when the bond is formed. So this is where one of the things that it talks about that anytime you are making a bond, you are going to be lowering down the potential energy. And when you lower down the potential energy, that means you are releasing the energy in that particular case. If this becomes hard to memorize that, hey, if I'm making a bond, how's the energy is released? Well, think of the other way. When you break a bond, you're actually going to be needing the energy. So that means forming a bond will be releasing the energy because they're just opposite processes. And if one process release energy, the other one must be requiring energy. It's like, let's say if you have a pencil, if you need to break a pencil, you actually need to put in some force, put in some energy to break the pencil. You can assume the bond the same way where if you are breaking the bond, you're going to be needing energy, but at the same time, the opposite, when you're making the bond, you're going to be releasing the potential energy. So the limitation of valence bond theory, I wouldn't really say the limitations, but typically you need some extra help to explain some of more these complex things in forming the bonds. And I'm going to take an example of carbon because that's going to be the most common thing that you're going to be seeing out there. So carbon has an atomic number of 6, which means its electronic configuration would be 1s2, 2s2, and 2p2. Now, I'm only going to be worrying about my valence shell electrons, which is going to be 2s2, 2p2. So if I go ahead and draw my orbitals in this particular case, I know I got one orbital in the 2s, and I know I got three orbitals in the 2p. So I will have two electrons in the 2s, and I got two electrons in the 2p. Now, based on the valence bond theory that we just talked about, if that was true, we would see that this carbon has only two half-filled atomic orbitals. So, as a result, it would be able to make two bonds because that was the whole point of the valence bond theory, that the orbitals that are actually half-filled, those are the only ones that are going to be overlapped to make a bond. So if that is true all the time, then carbon is going to be able to make only two bonds because in the ground state electronic configurations for the carbon, you only have two orbitals half-filled. So this is going to be the ground state electronic configuration for the carbon. Now, how many bonds carbon does really make? I can give you some examples like CH4, I can give you CCl4, and if you look at the Lewis-Strauss structure of CH4, we typically have carbon at the center and we got four hydrogens around it. And for CCl4, kind of similar, I would have carbon at the center and I would have four chlorines, and each of those chlorines will have octets completed. So just make sure you know how to draw the Lewis-Strauss structures for those. Now, what do you see right now? Carbon is actually capable of making four bonds, but based on the valence bond theory, which talks about only half-filled atomic orbitals will be able to make the bonds, it can only make two bonds. So this is where it kind of lags a little bit or fails a little bit, you can say, that it doesn't explain the formation of these extensive bond that you can see in case of carbon. And you can also see in case of maybe boron. So if I take an example of boron, which has an atomic number of 5, so that would be 1s2, 2s2, 2p1. So that is your ground state electronic configuration. So then I would have in the valence shell, I will have two electrons in the 2s and one electron in 2p. So based on that, based on valence bond theory, the boron is going to be able to make only one bond because it's got only one half-filled atomic orbital. But some of the examples I want to give you, the compounds that contains boron is like BH3, BF3. You can also have BCl3 and all that. So what do you see in all of them is boron is actually making three bonds. So how do we explain the formation of three bonds by boron and the formation of four bonds by carbon using the valence bond theory? Well, you can still use valence bond theory partially, but we're going to have to get a help of hybridization to explain how the four bonds in case of carbon are made and how three bonds in case of boron are made. Now, those are only two examples I'm taking, but there are some other atoms as well that are going to be better explained by the hybridization in terms of how many bonds they are making. So let's talk about what an hybridization actually is. So it's really the mixing up of the orbitals. So I have, let's say, carbon, which I talked about. I'm just going to go ahead and copy this. The ground state electronic configuration for the carbon here, rather, it's going to be 2s2 and 2p2, which I would have two electrons in the 2s and two electron in the 2p. That leaves this orbital right there empty. So what happens that there is going to be some sort of promotion of the electron. So I'm going to promote, and some books may also say excite the electron. So that would be an excited state electronic configuration. So in that case, what happens? One of the electrons from the 2s jumps on to the 2p, and now you get a set of orbitals where you actually have four electrons in those four orbitals. So now you got all of a sudden you got four orbitals that are actually going to be half-filled. Based on that analogy, based on this excited state electronic configuration after promoting the electron, now you can say that this carbon is going to be able to make four bonds, and that's exactly what happens. And you can use the same analogy to explain the formation of three bonds in case of boron, where I would say that one of the electrons from the 2s is going to get promoted onto the 2p, and as a result, you would have three half-filled atomic orbitals, and that's how boron makes three bonds. Now, once I get these promoted, I still got to mix these orbitals. Remember that. I didn't really mix the orbitals. I just got the electrons promoted from the 2s onto the 2p here so that I can have four half-filled atomic orbitals. Now, when it comes down to mixing the orbitals, I can mix the s and the p together. And now, how many you really need to mix from the s or from the p, that kind of depends on the need. I can mix all of them, let's say, if for a minute, if I mix all of them, so then I get a set of four orbitals. And that set of four orbitals would be having one electron each, and we call those sp3 hybrid orbital in this case. Now remember, I do not have to get all three orbitals to be mixed from the 2p subshell, but in this first example, I'm mixing all three of them. Let me give you another example where maybe I want to be mixing only, let's say I'm just going to use this different color here, so pay attention to the color. I'm going to be mixing one from the S and two from the P, so I get a set of three orbitals that are going to be hybrid now, and they're each going to have one electron. So that would be your sp2 hybrid orbitals. And then you're going to have one p orbital that is not the part of the mixing. Remember that. So that still have an electron that is still going to be able to make the bonding here, but we call this unhybridized p orbital. Now let me talk about what happened in terms of simple language here when you're mixing the orbitals. So this example right there, this picture right here, I got the 2s, or any s orbital, matter of fact, and I got three p orbitals here. The p orbitals, for the simplicity reason, they're just aligned in the same direction, but remember they are in the px, py, and the pz directions. So when I'm getting all four of those mixed, and that would be That would be this example right there where you have sp3 hybrid orbitals. Now I have a sphere and I have three dumbbells. So it's like mixing two colors. When you mix two colors, what do you get? You get something in between. Kind of same story here. When I'm mixing the sphere and in a dumbbell, I'm not going to have sphere left. I'm not going to have a dumbbell left. But what I'm going to have left, I'll have something in between. So these are, I don't know, what you want to say, kind of half dumbbell, or I can say it's kind of in a balloon where you have this side is the balloon and where you tie the knot, and you have the other side of the balloon basically here. So you have these four hybrid orbitals that are kind of, let me just change the color here. These four hybrid orbitals that I just made here, they're gonna look like this in terms of the direction, in terms of their shapes. So this is going to be the shape of these sp3 hybrid orbitals. And then this picture represents their drawing in the 3D basically. Remember what I said, that these p orbitals are not aligned only vertically, but you will have one on the x-axis, one on the y-axis, one on the z-axis. So eventually this is what you're going to be seeing in a set of sp3 hybrid orbitals. To better explain that, I have another picture here. So remember, this is the 2s from the carbon. This is one of the two p's, so this would be 2px, this is 2py, and this is 2pz from the p orbitals. So remember, these are in three different directions. When you hybridize those, you're going to get a set of four hybrid orbitals, and we call those sp3. So I'm getting 3 from the p, that's why there isn't a 3 on the exponent here. And I'm getting only 1 from the s, so that's why there's nothing on the exponent for the s. So these are your sp3 hybrid orbitals that you're going to be getting in this particular case for the hybridization here. Now let's talk about how the sigma bond is made. So we have, I can probably take this example as well. I'm just going to go and copy this. Okay, so if I am making, let's say, CH4 for a minute. So in a CH4, this is the Lewis-Dot structure. And since I have four bonds around the carbon, that gives you that it must have four hybrid orbitals in there. So we'll talk about that in a minute as well. But then focus on what is coming from the hydrogen. Now, hydrogen only have 1s1 orbital in there. So it's just in a sphere. So I have these three sp3 hybrid orbitals from the carbon. And then from the hydrogen, I'm going to be getting this s orbital that's going to be overlapping end to end here. So these are your four hydrogens that are going to be overlapping. And this overlapping region right there is where you are having the electrons shared, and this is where you're making the sigma bond. So this is the formation of a sigma bond, which typically talks about the end-to-end overlapping of hybrid or atomic orbitals. Most of the time hybrid orbitals, but then remember, in case of hydrogen, you don't really hybridize anything because hydrogen has only one orbital. So you can also have atomic orbitals, especially in case of hydrogens here. Another example I have here, how do you make a carbon-carbon single bond, let's say, or carbon-carbon sigma bond? And I got this picture right there where I got two carbons that are about to get hybridized, and they will eventually get this end-to-end overlapping. So what I see right now here, I see this is one of the balloons here. This is another balloon right there that's kind of pointing in this direction. There's another balloon right there. But then you also see one orbital right there that has not changed its shape. So the orbital that has not changed its shape is actually going to be your unhybridized p orbital here. So remember that. So if I go back to this step here where I said, even though I have a total of four orbitals that can be hybridized or mixed, I don't necessarily have to use all four of them. I could use one from the S and two from the P, and as a result, I make sp2 hybridization here, which means I would have three orbitals with the balloon shape, and then one of the p orbitals would stay unhybridized. That would still be in a dumbbell shape. So I'm gonna make sure I write down this would still be in its original shape. And that's exactly what's happening here. this carbon having three hybrid orbitals, so that tells me that this is actually going to be in an sp2 hybridization, and then you have this unhybridized p orbital that's still going to be right here. So now the hybrid orbitals from these two carbons right here, they're going to be overlapping with one another end to end, and this is where the sigma bond is kind of formed. Change the color here, maybe. This is where the sigma bond is formed, where you have one electron pointed up, one electron pointed down. You still have a one electron on those carbons that are on those unhybridized p orbitals, but we're not making the sigma bond out of those. Remember, the sigma bonds are typically made from the hybrid orbitals or from the atomic orbitals in case of like hydrogen atoms when you don't really hybridize anything. Now, what happens? What happens with this unhybridized p orbital that still carrying one electron on each of these carbons here? Now, that would actually do in a sidewise overlapping and eventually makes the pi bond. So this is actually an example of, let's say, carbon double bond C and hydrogen here and hydrogen here. So since I have three electron domains around each of those carbons. So this is one of the electron domains, this is another electron domain, this is another electron domain. In specific, those electron domains are the bonding domains. I don't have any lone pairs or not or non-bonding domains there. So carbon has only three electron domains. So one of the easiest way to figure out the hybridizations is find how many electron domains you're gonna have around that atom. So since I have three electron domains here, so you must have three orbitals to be hybridized. So I need three orbitals to be hybridized, which means I'm going to start from S. So remember, in carbon, you have 2s and the 2p being hybridized. And then eventually I'm going to move to p until I get a total of three hybrid orbitals. I can only get one from S because remember, any S subshell have only one orbital. Any p subshell will have three orbitals in total. So I'll have one from the S and I'll need two from the P, and that gets you an sp2 hybridization. So both of these carbons right now, they are actually sp2 hybridized. And we kind of explained that here, that these three balloons shaped hybrid orbitals tells you that it's an sp2 hybrid, and one of the p orbitals that's staying unhybridized on the carbon is going to be just the p orbital. So those two, each of the carbon has two hydrogen atoms, all right? So those two hydrogen atoms would be doing end-to-end overlapping here. So you can see right here, you're doing an end-to-end overlapping here, you're doing an end-to-end overlapping with these hybrid orbitals. So those are actually making the sigma bond. I would have one sigma bond here, I would have one sigma bond here, I would have another one, another sigma bond here, another sigma bond here, and then you're also doing the end-to-end overlapping between the two carbons. That's another sigma bond. So you can see how many total sigma bonds I have here. Let me just go and count them up here. That would be one, two. One of the bonds in the double bond is going to be a sigma bond. That's three, four, and five. So I have five sigma bonds in this particular case. And then how the pi bond is going to be made. Let's talk about that. Now you got this unhybridized p orbitals on each of those carbons that's also going to be carrying one electron. So I got one electron right here and I got one electron right there. I'm going to make those with an opposite spin here so that they can overlap. Now right now you see those are kind of far away from one another, but in real life at the microscopic level, these orbitals are going to be fairly close to one another where they're going to sidewise overlap with one another. So these will sidewise overlap with one another, and that's something you would see right there. So this sidewise overlapping where you see this overlapping region, uh, that's where your bond is going to be formed. So that sidewise overlapping of hybrid orbitals is of unhybrid orbitals rather is going to be the one that's going to be making the pi bond. So in the double bond, you will have one pi bond in there. So remember the difference between the sigma and pi bond? The sigma bonds is an end-to-end overlapping of typically hybrid orbitals, but sometimes just atomic orbitals as well. like in case of hydrogens. And then in case of an pi bond, it is going to be in a sidewise overlapping of unhybrid orbitals for the most part. Okay, it typically, if you have one single bond, so one single bond is made of one sigma bond. If you have one double bond, in one double bond you have one sigma and one pi bond. So make sure you know that. But then if you have one triple bond, in one triple bond you'll have one sigma bond and two pi bonds. Make sure you remember that. Now, do you really have to write down every single thing, or do you really have to write down this drawing and whatnot to figure out what's really going to be the hybridization? The answer is no. You can figure out the hybridizations even from the Lewis star structures once you have drawn the Lewis star structures. And let me give you a few examples here. Let's talk about the CO2 here. If I go ahead and draw the hybridization, the Lewis star structure for CO2, and I'm going to go ahead and do that quickly because this is something that you should know already, how to draw the Lewis star structures. So the Lewis star structure for the oxygen and for the carbon dioxide should look like this, where you want to make sure the octets are completed and whatnot. Now I want to count the electron domains on all of them. So the electron domains on the carbon here would be only two. So because I got two bonding domains, and those two bonding domains only will eventually give you two electron domains total. And what I said, if you have two electron domains total, that will give you two hybrid orbitals. And if I need only two orbitals to be hybridized, that means your hybridization is just going to be an sp. So carbon here is just going to be an sp hybridization because right now on the left side I got in a double bond, on the right side I got in a double bond, and in one double bond you only have one sigma and one pi. So I got only a total of two sigma bonds altogether in there. I can also figure out what's going to be the hybridization for these oxygens. Let's talk about that. So oxygen has one bonding domain, that's on the right side in this case. Even though if you have a double bond or a triple bond, you still consider that as in one bonding domain. But then, in addition to one bonding domain, the oxygen actually has two non-bonding domains, or you can also say two lone pairs on that oxygen. So that would be two non-bonding domains. So what that gives me in total, that gives me a total of three electron domains in total. So if I have three electron domains in total, this tells me that I need three atomic orbitals to be hybridized. So three atomic orbitals to be hybridized here, that gives me a hybridization of sp2. I'll get one from mass and I get two from p to get a total of three orbitals hybridized. So this would have sp2 here, and this would also have an sp2. So this tells me that carbon having only an sp hybridization, you would have two unhybridized p orbitals. If I have two unhybridized p orbitals here, which are just going to be the dumbbells, and each of the oxygens actually has one unhybridized orbital, because remember, I already got two from the p, so there's only one remaining in there. So one unhybridized p orbital. So I don't want to draw that here, but think of this. I got two unhybridized p orbitals on the carbon. So one of the unhybridized p orbital on the carbon is going to do the sidewise overlapping with one unhybridized orbital on this right oxygen, and that makes the pi bond in that case. And then the other unhybridized p orbital on the carbon will do the sidewise overlapping with the unhybridized p orbital of this left oxygen atom. And that's how you make the pi bond on the left side as well. So this CO2 at the end of the day will have two sigma bonds and two pi bonds in total. All right, let's look at maybe HCH here. HCCH. If you draw the Lewis star structure and if you figure out the valence electrons and whatnot, to satisfy the octet rule, you will end up getting a triple bond between the two carbons. There's not going to be any other way to satisfy these octets. Now, if I want to look at what is going to be the hybridizations for these carbons, I only have two electron domains around each of those carbons. I got one on the left, one in the middle here. Even though it's a triple bond, we're still going to count that as one electron domain. So since I only have two electrons domain in total, which is made of only the two bonding domains, there's no lone pairs or the non-bonding electrons on the carbons here. So this tells me I only need two orbitals to be hybridized, and for that reason, this carbon is going to be an sp, and this carbon is also going to be an sp hybrid carbon. So that means you have two unhybridized p orbitals on this right carbon, and you also have two unhybridized p orbitals on this left carbon, and those two unhybridized p orbitals on each of those carbons will overlap with one another to make a set of two pi bonds in there. Because remember, in a triple bond, you have only one sigma, but then you got two pi bonds in there. All right, so this is what it's going to look like in that case. And how many sigma bonds I have? So sigma bonds here would be 3. That would be one right here, and one of the bonds in the triple bond would be sigma. And then how many pi bonds you have? That would be just 2, because one triple bond would have 2 pi bonds in there. If I take an example of PCl5 here, let's talk about that. If I draw the Lewis star structure, you would see this is how it's going to look like. So make sure you draw the Lewis star structure for the PCl5 first. And just based off the Lewis star structure, you should be able to figure out what's going to be the hybridization. I want to go ahead and count the electron domains around the phosphorus here. So I would say there's no lone pair on that phosphorus, so I have a total of 5 electron domains. Since I have 5 electron domains in total, all of them coming from the bonding domains, I must have 5 orbitals being hybridized. So these 5 orbitals hybridized, that means it would be s. I can only get 1 from s, because remember, any s subshell will have 1 orbital only. I'll get 3 from the p, so that would be sp3. But remember, I need 5 in total, so where would I go after the s and the p? Well, we got to go to the d, so I will need 1 from the d to get a total of 5 in there. Now, how can we get d in this particular case, or in case of phosphorus? Now, phosphorus has an atomic number of 15, which means I have its valence shell electronic configuration, which is going to be after neon. That would be 3s2, 3p3 basically. So I have 2 electrons in 3s and 3 electrons in the 3p, but we don't really write it down. But remember, there is a 3D subshell that actually exists that does not have any electron. So that's why we're able to use the D subshell or the D orbitals in case of atoms that are going to be on the third period and below. So that's why phosphorus can exceed the octet, sulfur can exceed the octet, iodine can exceed the octet, and whatnot for those reasons, because they got the D subshell that's empty, where the electrons can be promoted onto the D subshell. And now you would have multiple or more than 4 atomic orbitals with with only 1 electron. In case of like IF7, if you draw the Lewis star structure, I'll have iodine in the center, and I got 7 fluorines. So that's 6. I got another one. Each of the fluorines would have octet completed, to make sure you actually first draw its Lewis star structure, understand it well. Now, how many electron domains I really got around the iodine here? So if I want to focus on that, that would be 7 electron domains in total. All of them coming from the bonding domains. There is no lone pair on that iodine at the center. So that means I must have 7 orbitals hybridized. Now, how do I get 7? Well, I'm going to start from mass, obviously. I can only get 1 from mass, and then I'll go to the p. How many I can get from p? I can get 3 from p. So that's only four so far. I still need three more, so then I go to the D, so that would be sp3 d3 because I need a total of seven hybrid orbitals. Let me give you another example, such as like NH3. So if you draw the Lewis star structure for NH3, this is how it looks like, and typically have a lone pair on that nitrogen at the center. So that means I got one non-bonding domain, or one lone pair, you can say, and then I got three bonding domains on the nitrogen. So that gives me a total of four electron domains in total. So if I have four electron domains, that means I need four orbitals to be hybridized. And if I need four orbitals to be hybridized, I'll start from S and then I'll go on to the P to get a total of four. So it would be an sp3 in that case. Now the hybridization you would also see in the Vesper theory where, if it's an sp3 hybridization, the electronic geometry is typically going to be tetrahedral. The shape could change depending on whether you have only the bonding domains or the non-bonding domains. So that's another video I have posted, so make sure you kind of watch that. But this is just to kind of explain how the hybridization and the valence bond theory actually works together.